Having explained the phenomenon of confounding in the previous video, we now turn to the solutions. What do we do if we've got confounding in our data, especially when we're dealing with observational studies? This is very common. Well, we know that we can address this through stratification, standardization, and regression modeling. In this video, we will mainly focus on stratification. Standardization is not part of our syllabus. However, if you're interested, there's a very, very good explanation given at in the appendix of Ehrlich and Joubert, appendix number 1. So you could go and have a look at that. It's very easy to understand. And in the next module, HME 712, there will be more coverage of the topic of regression analysis towards the end of that module. Now, of course, if we can, we would like to get rid of confounding before we even start to collect data. Then we don't have to worry about it. Not always possible. So in the study design stage, there's some proactive things we can do. We might decide to rather go for a randomized or experimental study design. We might decide to do a matched case control or a matched study design. You can also do something called propensity score matching. Or we might want to restrict the study sample just to include people of a particular sex or age or socioeconomic status and so on, in order to avoid confounding due to those variables. And then, of course, if we find that that's not feasible, then we still have remedies at the data analysis stage, and those are stratification, standardization, and regression analysis, or so-called modeling. So let us begin with the proactive steps. The first of those was randomization. We could do a trial, an experimental study. And what we do there is we randomize the study participants, for example, by tossing a coin to see whether they go into the intervention group or the control group. This means that any confounding variables that are present will be equally distributed in the two comparison groups. Therefore, the effect of confounding will be nullified. You'll remember from the previous video that we said that the problem of confounding arises because the confounding variable is unequally distributed in the two groups being compared. Whereas that is true in many cases with observational studies, with a randomized controlled trial or an experimental study, we control this so that the confounder is present in the same rate or proportion in both the intervention and the control group. The other two things that we mentioned at the proactive stage, if you want to prevent confounding in the first place, were matching and restriction. Now, with matching, you match your controls to the case. So if the case happens to be a 36-year-old woman, then you select a control, or you could have more than one control if you require more than one control, who is also a woman and also aged approximately 36. Then age and sex would not be a problem anymore. They shouldn't cause confounding if you match age and sex out. You could also match for smoking status, parity, and so on, as the case may be. This does lead to analytical complexity. So please, if you're deciding to do a matched study, do get some expert inputs. Now, with regard to restriction, you limit entry into your study. So I'm only going to study women aged between 30 and 50. I'm not going to include any men. I'm not going to include women who are younger than that age group or older. Now, that's a very good way to exclude those confounders, if there are potential confounders, but it would limit the generalizability of your results, of course, so there's a bit of a drawback. We turn now to the situation where we were not able to be proactive because of expense or complexity or because we wanted greater generalizability. Now we have to deal with confounders at the analytical stage. We've collected the data. Now we have to adjust for confounders in our data. So we could attempt a stratified analysis, we could do standardization, and we could also do regression models. In order to perform stratified analysis, you stratify your data according to the confounding variable present or the confounding variable absent. So with regards to alcohol and lung cancer, where smoking was the potential confounder, we will perform the odds ratio for smokers, and we'll do the same for non-smokers, but separately. So these will give stratified odds ratios, and they will be unconfounded by smoking status. Now, there's no known statistical test for a confounder. However, we do have some workable rules of thumb. What you do is you look at the stratum-specific associations, the odds ratios, and if they are similar in value, and they're both either greater than the crude odds ratio, the crude is when you've got both groups combined, or they're both lower than the crude odds ratio, and they differ from the crude association or odds ratio by more than 10%, then this is very suggestive of confounding being present. And it would be wise then to perform regression analysis, for example, including this confounder so that you can adjust for the confounder. We say when a confounder is present that we demonstrate Simpson's paradox. I'll explain a little bit later. Now here's a hypothetical data. So we have alcohol and lung cancer and smoking as the confounder. So we've stratified by smokers and non-smokers. The crude or combined odds ratio was 2.2. The stratum-specific odds ratios were 1.02 and 1. So in other words, the odds ratios, when we stratified, moved together. They're both very close to each other, and they moved on the same side of the crude. They were both lower than the crude odds ratio. We went from 2.2 to 1. So that movement was greater than 10%. So this is strong indication that confounding is present. The Simpson's paradox refers to the fact that the stratum-specific odds ratios are 1, and yet when you simply add those numbers together, you would expect then the combined odds ratio to be 1, but it turns out to be something else, 2.2 in this case. So that's a paradox. And when you see that paradox present, then you know there's probably confounding present in your data. If you want to use standardization to adjust for confounding, what you do is you work out the age and sex specific rates amongst the controls and the cases, and then you apply those age and sex specific rates to an artificial population structure that is common to both groups. So that you remove the differences between sex and age composition, you remove that by applying an artificial population, and then you compare that artificial rate between the two groups. We're not going to talk about that more in our course, but if you, as I said, if you're interested, go and read Ehrlich and Joubert. It's a very good explanation. Finally, regression modeling or regression analysis is a very common and popular way of dealing with confounding in observational studies. So you can control for one or even more confounders at the same time, and it allows you to estimate the adjusted odds ratios for each association measure and each covariable. You're going to learn more about this in HME 712. Right towards the end of that module, we cover linear and also logistic regression.